Okay, this is a video to help you with Lenz's law and to explain things a little bit, hopefully a little bit more deeply or else again, so that you get a better feeling for what's going on. Lenz's law basically says that when a metal is present, or when a conductor is present, in a changing flux, the conductor, this is a magnetic flux, by the way, the conductor will create currents or generate currents that create new magnetic fields that oppose the change in the old magnetic field. Okay, you can barely see that, but that's what Lenz's law is telling us. All right, so let me give you an example. Let's say we have a coil of wire like this, and a magnetic field that is slowly getting stronger. So at first it's weak, so it's a little one at first, and then a little while later it gets stronger. This is the B field. So as the magnetic field gets stronger, Lenz's law is telling us that currents are going to be generated in the coil to oppose this strengthening of the magnetic field. All right, so for instance, in this case here on the left, the currents are going to want to generate a magnetic field that is saying, hey, it's basically going to try to act against the current magnetic field that's getting stronger. So it's going to generate a magnetic field in the opposite direction. And then there were a lot of questions as to how do you know what direction the currents are? Well, we can use the right-hand rule. The magnetic field is going to be generated in a loop, either in one direction of the loop or the other direction of the loop. And if the currents are moving, let's say, counterclockwise, that's the symbol for counterclockwise, I'll wrap my fingers in the direction of the counterclockwise circulation of the currents, and that would mean that the magnetic field is coming out towards me. On the other hand, if I'm looking at a clockwise circulation of the loop, of the currents in the loop of a piece of wire, then the magnetic fields are going to be using my right-hand rule and bending my fingers in the direction of those currents. The magnetic field is going to be pointed into the board. Okay? So that helps me figure out, then in this case over here, what I'm going to do. My magnetic field is pointed downward, so I point my thumb in the downward direction. So the currents, in order to create that magnetic field in the downward direction, they have to be moving in the clockwise direction around this loop right here. The currents are the ones in red, and they are in the clockwise direction. I'll erase that arrow there. Okay? So I'll give you another example. Let's say I have a loop. And I have the magnetic field directed that way, but it's getting weaker. So this is step 1 here, and this is step 2 here. All right, but the magnetic field is getting weaker. So it starts out stronger, and then it gets weaker. What are the currents going to do in this case? Well, if you have a strong magnetic field, it's getting weaker. The currents want to create a magnetic field to try to sustain the one that's there. They don't want it to get weaker. So they're going to do this. They're very conservative. They want to keep the way things are. So the currents are going to generate a magnetic field that is going to be in this direction, that I've pointed with the red arrows. So if I want to figure out what direction the currents have to be, whether it's clockwise or counterclockwise, well, I point my finger in the direction of the red magnetic field lines, and my fingers are going to point in the counterclockwise direction in this case. So in this case, the way I've sketched this, I'm assuming that you're basically seeing the loop more or less kind of edge on here, not quite edge on, but partly. This is a three-dimensional drawing that I'm trying to, or three-dimensional situation I'm trying to draw in this two-dimensional diagram. But hopefully you can see that the currents would be counterclockwise in that way, and that they would generate a magnetic field in the direction of the arrow as shown. Okay, hopefully this will help you as you think more about Lenz's law.